Okay guys, this is going to be your Chapter 4 Work and Energy Study Guide key. So for question number 1, work is a force applied over a distance. So the next question, if you push a desk and it doesn't move, have you done any work? And explain your answer. If the definition of work is a force applied over a distance, and then you push a desk and it doesn't move, it hasn't covered any distance, which means no, you did not do any work. The object has to move in order for work to be done on it. Question number 3. There are 2 things that have to happen in order for work to be done, and what are they? These can be in any sort of words, but basically the first thing is the object has to move. In other words, cover a distance. The second thing is that movement has to be in the direction of the force applied to it. So question number 4. When you lift your backpack, have you done any work? In that case, the force that you're applying to your backpack is up, and the backpack also moves up, which means yes, you have done work. Number 5. When you carry your backpack to class, have you done any work? My answer is no, because when you're carrying your backpack, the force that you apply to the backpack is up, but you're walking left to right. So you have not done any work because the force and the direction of motion are not in the same direction. Number 6, the equation for work and draw the triangle. Well, first of all, the equation for work is right here. Work equals force times distance, which means that your triangle has to have work in the top, force and distance in the bottom. So now that we have that, we need to make sure that we know the units for everything, because if we don't put our units on our calculations on the test, those are points that you should have had that you're not going to get. So first, your units for work has to be in joules. Units for force is of course in newtons. We've done that a million times. And then the units for distance has to be in meters. So number 7 is using this equation and the triangle to solve a problem. So number 7 says a couch is pushed with a force of 80 newtons and moves 5 meters across the floor. How much work is done when you move the couch? If we know that work equals force times distance, we just need to sub it in. We know that the units for force are newtons, which means that's them right there. And we know that the units for distance are meters, which means that's it right there. So we're just going to take 80 times 5, and we're going to come up with our answer, 400. Don't forget the units for work, which are joules. And then number 8. How much work do you do when you lift a 100 Newton child 0.5 meters? So, again, we just have to remember our units, and that'll tell us kind of what to do. We know that work equals force times distance. Force has the unit of newtons, which means that's it right there. Distance has a unit of meters, which means that's it right there. So we're going to take 100 times 0.5, just like this, and we're going to come up with our answer, which is 50 joules. Do not forget units. Number 9, suppose you give a book a push and it leaves your hand and slides across the table for 1 meter. How long did you do work on the book? I actually demonstrated this in class, and you guys got this absolutely right. You only do work on the book while your hand is in contact with it. Number 10. Definition of a machine. A machine is a device that changes the force or increases the motion from work. And so, machines can change the way work is done by doing 3 things. First one is that they can increase the speed at which work is done. Second thing is they can change the direction of the force needed. And the third thing is that they can increase the force that we put on the object. Question number 12. Does a machine change the amount of work that is needed to complete a task? This is something that is most definitely going to be on your test, and you definitely need to know it. it doesn't matter if I use a wrench to remove a screw, or it doesn't matter if I use my hand. The work required to remove that is going to be the same. It's just that the machine makes it easier for me. So, no, they do not change the amount of work that's needed to complete a task. They do not change the amount of work. What they are able to do is change how we do the work, so they make it easier on us. So number 13, explain how using a ramp makes lifting a box into a truck easier, and use math to explain your answer. I kind of went over this in class, but I think it's important to go over it one more time. So I made two sections, one without the ramp and one with the ramp. In both cases, you need to do 20 joules of work in order to get the box into the truck. Okay, either way you have to do 20 joules of work. So then we just have to think about how the ramp makes the situation different. So without the ramp, if we think about it, work equals force times distance. So without the ramp, and if we have to lift the box into the truck ourselves, it's going to take a good amount of work over a short distance. So we're going to say that it takes, it takes 10 newtons of force, okay? It's going to take a good amount of force over a short distance, about 2 meters. And that's going to give us our 20 joules. So we completed getting the box up into the truck. But with the ramp, something changes. And so we have to think about what it is. If we were to use a ramp to get the box into the truck, it's going to increase the distance that we have to cover. So we have to keep that in account. So it may make the distance 5 meters. But since we have to do 20 joules of work, the amount of force needed actually goes down, making the whole situation easier. So we would only have to expend 4 newtons of force, and we would still get the 20 joules of work, making the box actually go into the truck. Question number 14. All machines are 100% efficient, true or false? That's absolutely false. There is no machine that is 100% efficient. Number 15. How can we make machines more efficient? The thing that we talked about in class is to do something to decrease the force of friction. And number 16. The definition of power. Power is the rate at which work is done. Now you may have a different definition that you've written down, something like the rate at which energy is converted. Well, in reality, this is it. It's the rate at which work is done. Because in the end, the equation for power is the amount of work that we do over the amount of time that we do it. So work divided by time, which means that your triangle is going to have power down here in one of the corners, and if you cover it up, like I did right then taking work divided by time solves it. So now we have to deal with our units. The units for power are the watt. Units for work, once again, is the joule, and then the units for time in this case is going to be seconds. Now, number 18 says you do 950 joules of work to push a sofa, and it took you 5 seconds to move the sofa. What was your power? So we know that the equation for power is work divided by time because we just wrote it right there. So if we think about that, and we know that the units for work is the joule, which means that's our work right there. And the units for time is seconds, so we have work and we have time, so we just divide them. 950 divided by 5 gives me 190, and don't forget your units, which is the watt. Number 19, the definition for energy. The ability to cause change can also be described as the ability to do work, because work causes change. Number 20, the units for energy are joules, which is the same as the units for work. Number 21, definition for kinetic energy. Energy due to motion. Anytime you see the word kinetic, it means movement or motion. That'll come back around, so don't forget it. Number 22, the amount of kinetic energy an object has depends on its mass and its speed. So the higher the speed, the more kinetic energy. Potential energy is energy that is stored. And so that could mean that it's stored in chemical bonds, which means that it's chemical potential energy. It could mean that it's stored because of its distance above the ground, which is normal potential energy, or it could mean that it's stored within the tension of a spring or a rubber band, which would be elastic potential energy. All of those are stored energy. So now, looking at the pendulum, our first question is, at what point the pendulum has the highest kinetic energy? So, thinking back to what I just said, the higher the object's speed, the higher its kinetic energy. And this pendulum is going to pick up speed as it swings, so the highest kinetic energy is actually right down here because it'll start to slow down due to gravity on the way up. So, point C is where the pendulum has the highest kinetic energy, while point A is where the pendulum has the highest potential energy. Point A is the place where it's the furthest from the ground. Number 25, as the pendulum falls from point A to point C, so between here and here, potential energy is actually going to be decreasing because we're getting closer to the ground, while the kinetic energy is increasing. Remember from your lab, you could watch them go opposite directions like this. Number 26, chemical potential energy definition. That's the energy due to chemical bonds. So that is the energy that we have within our bodies. So anything that we cause is due to chemical potential energy. So when we push a book, our chemical potential energy is transformed into kinetic energy through the motion of the book. So down here, when an object is burned, chemical potential energy becomes both thermal energy but also light energy. Number 27, law of conservation of energy, says energy can't be created or destroyed. But what it can do is transform from one form to another. So just like I talked about, we had our chemical potential energy in our body transferring to kinetic energy in a book. Number 28, definition of mechanical energy, I kind of simplified it down. Mechanical energy is the sum of kinetic and potential, so I just simplified it to kinetic energy plus potential energy equals mechanical energy. Very important to know that mechanical energy of a system often remains constant. So in other words, it stays the same. So when you're filling out those little boxes with potential, kinetic, and mechanical energy, keep that in mind. Number 30 all has to do with this diagram right here, and similar to the pendulum. So which position does the ball have the most potential energy? Potential energy is highest at A. Yes, A is higher than G. Letter B, potential energy from point B to point D, so between here and here, is actually decreasing, getting closer to the ground once again. Letter C, where does the ball have the least potential energy? At the bottom, D, where it's closest to the ground. Letter D, the kinetic energy from point B to point D, so here to here. What's happening to the ball? It's speeding up, which means that the kinetic energy is increasing. Letter E, kinetic energy from point D to point F. Well, the ball's going to pick up speed from here to here, and then as it starts to roll up this side, it's going to get slower and slower, which means the kinetic energy would have to be decreasing. Okay guys, we're on the home stretch here, and this is what I was referring to when I was talking about mechanical energy. We saw that mechanical energy is potential energy plus kinetic. And we also read that mechanical energy stays the same. So throughout this whole process, the mechanical energy stays the same. So all across the board, I should know 150, 150, 150, 150, all across the thing. And if we know that potential plus kinetic equals mechanical, I know that this has to be 150 and 0. This has to be 90 and 60, 0 and 150, 140 and 10. Alright, so now we have some energy transformations. And the first one is a flashlight. And you had a couple of options for how to start. You could have put that it begins with electrical energy, or you could have put chemical potential energy, because technically batteries operate off of chemical energy and produce electrical. So I would take either one of these to start. So you have to think about, during energy transformations, what's causing the machine to work. So that's one of these two things you could pick. And then what's the purpose of the machine, and that'll tell you what type of energy it's giving off. So in this case, our electrical is being converted to light energy. The purpose of a flashlight is to provide light. But also thermal, because that light bulb heats up a little bit. So then if we think about a bicycle, in order to make the bicycle work, we have to pedal it, which means our energy is what's going into it, and we talked about that being chemical potential energy. And then the point of a bicycle is to move, which means our chemical potential energy is being transformed into kinetic. All right, that's it. Study hard, everybody.